what we're going to be going over here is a determinant. And we're going to look at this determinant in terms of a geometric volume here and really look at it from the visual perspective here. And the determinant we're going to be dealing with is like the production function here, similar to the Cobb-Douglas production function. So this is our production function. I'm only showing it because I'm looking at it in reference to how we set up our determinant here. So we're going to have some revenue output here, and that would be some inputs here of material and labor times some quantity here of dollars for per unit of sales here that we have, and then we'd be subtracting from it some costs here for both material and labor based on some constraint here. But nonetheless, what we would do here in this case, we're going to set up a 3x3 matrix determinant based on the second partial derivatives here of this production function, just to understand what it is. So this is going to be our matrix determinant here. It's really referred to as a Hessian matrix here. So you get see some numbers here in your top column here and your rows here, your rows here. And then along with that, this matrix here, based on those second derivatives, you're going to see some algebraic function here. We're going to have material raised to some exponential amount, labor raised to some exponential amount, and then they are sitting either in the numerator or the denominator of these second partial derivatives here. But nonetheless, that's what we're going to be dealing with here. So we would solve this determinant here, and just looking at it in terms of the multivariate determinant or the algebraic solution, you're going to get some numbers like this, some quantities of material and labor here raised to some exponential amounts, both in the numerator and denominator. Okay, so what we would do here, just for our example here, just say, for example, we're using 78 units of labor here, 69 units of material. We plug those into our determinant solution here, and this is going to give, or into our matrix, excuse me, our 3x3 matrix up here, and it's going to give us a numerical block here of numbers as the solution for our matrix up here. So based on those inputs we have. So you can see we've got some numerical solutions here and just in numbers. Okay, and if we solve this determinant here, you're going to come up with just a single number or a volume that we're going to be looking at. So we've gone from the case here where we've got this multivariate determinant here. We broke it down into some linear numbers here, or some single numbers, a block of numbers, and it turns into just a single number and a volume. And that's what we want to get the understanding of. Okay, so going over here, let's look at it. So what we have here, we're going to be just looking at three different outputs here, and really just be concentrating on this middle or mid-range value here for, in this case, our production function here. So our production function, I'm showing that here in blue here, and then we've got three separate points here, and that's really, they're following the gradient path here, and for each of those points there's a tangent plane here. Okay, so that's what we're going to be dealing with here. And along with this production function, we have a determinant here. So what I've done here is I've just plotted the determinant out here, this light bluish, greenish volume here I'm showing. It's just that multivariate solution that we were looking at. Let's just look at it. That's this multivariate algebraic solution here. That's the matrix determinant matrix solution here. So what we can look at here, just matching it up with our production function, this first initial point here where we have our initial amounts of material and labor we're putting in our production function. So our determinant, I'm showing it in yellow here. That's going to be our first point here for our determinant. And what we do here, as we move along that gradient path here and increase our output, our determinant is going to work sort of in the same way here, but it's going down, whereas you can see, well, this our gradient path is increasing here, but it's leveling off at a different slope here. And our determinant follows sort of the same pattern here. It goes down at a very steep rate here, and as we increase our outputs of material and labor, it follows down, and the slope becomes less and less. And we have a change in slope, and this change in slope actually, we're looking at a rate of change here. Okay, so that's what we're going to be dealing with here. Okay, so let's go up over and look at it this way here. So we're going to look at this determinant as a rate of change here, really in volume here. So what I'm showing here is really sort of a vector field here. So this initial point, that was our initial point here for our inputs of material and labor here. And this is based, again, on our determinant function here. So what we're showing here, at that initial point, you can look out here at these arrows. They're very big arrows here, and they represent the size or the rate of change in this case, and that's really our volume that we're going to look at. So we're really looking at the change in volume here. And these arrows also show the direction here. So if we follow down our gradient path here, or our path here of our greatest increases here in our for our material and labor here, or the maximum output, or the different outputs here, you can see what's going on here. So at our initial point here, again, the arrows are very big. They're all pointing in the same direction here. And then we come down to our second output. But you can see here, those arrows are getting really small, that vector field we can see. So that's saying our change is less and less here, and that really represents, you're going to be looking at the volume here. So our change becomes less and less here as we increase our inputs here of material and labor here. So the vector field tells us the direction here, and also it gives us the change in volume, and we're going to look at that change in volume here. So what we're talking about here in the change in volume, you're really, when you're dealing with this 3x3 matrix here that we have, it's really just a parallelepiped here, or a parallelogram here. So you're going to have, we're going to be dealing with three different inputs, or three different vectors here that we deal with. So at this point here, where we have our initial inputs for material and labor here, we're going to have a larger and larger volume here. So as we decrease or increase our inputs of material and labor, our volume is going to change, and our volume is going to get less and less here. Okay, so that's what we're going to be dealing with, this volume, just to get an understanding of what we're talking about here. And if we move down here, just another view of what we're looking at here, we had this initial point here, initial amounts of material and labor here. So you can see our arrows again pointing in that direction. The arrows are very big here. So that's telling us that our volume at this initial point here is going to be very big. It just carries across here. But as we move down here, or increase our inputs of material and labor here, we get to that midpoint number here, that initial midpoint value that we're looking at. You can see the size of the arrows. Very small. Again, pointing all in the same direction here. So this is a vector field plot. It gives us an idea of both the magnitude of our volume, or our change in slope, essentially, we have here with this determinant, and it also gives us our direction. So as we move down our gradient path here, or we increase our inputs for material and labor, those arrows here are getting smaller and smaller. So we're getting less and less change, and it's going to be a less and less change in slope. Okay, so that's what we're going to look at. So let's go in, let's make our calculations now. Now for our calculations. So this is our determinant function here, and we'll follow our gradient path down here along our determinant function. And we're going to come to a point here that we're going to be looking at here, and it's really that midpoint here. And really we're looking at the determinant here as a change in volume or a change in slope as we move down our gradient path. Okay, so moving over here, let's look at this determinant matrix. And remember, that was that 3x3 matrix. Really, we're talking about three vectors here in vector space. So we're going to be looking at x, y, z coordinates here. Okay, so for our case, we're going to have three columns here and 3 rows. So really, our columns and our rows are equal here as far as numeric numbers here in this matrix. So let's just look at it in terms of rows here. So we'll look at row 1, row 2, and row 3. So row 1 here, it has a vector coordinates here, and everything starts with 0 here. When you're dealing with these determinants, remember you start with a 0 point here. So for your x coordinate, you'd have 0. Say a y would be 200 and z would be 350. So that, moving over to our vector here, this red vector, that would represent here row 1. And then looking at row 2, well, we go 200, then a minus 1.6, and then 1.3 here, decimal points here. So our row 2 is really this blue vector here, starting at 0 here and moving in this direction. Now, we also have row 3 here, so that represents 350 here, and then you have 1.38 and minus 2.46. So those this green vector is represented by that here. And actually that green vector starts here at 0, but I can't plot them here over the top of each other here. So really what we're dealing with here when we talk about this parallelepiped here, we're going to have row 2 and row 3 here. They're really overlaid or over each other here. So that's the problem we look at here when we try to represent them geometrically. Okay, so let's move over here and let's look at this matrix or this determinant matrix in terms of this volume here. So what we're going to calculate here is we're going to have a volume. We actually calculated with the determinant 497,300 at point 69 and 78 here. 69 material, 78 units here labor. Okay, so let's just link this determinant here, and it's really a parallelepiped here. And in our case, what we're going to be looking at here, we're going to really have a squashed down parallelepiped or parallelogram here. So let's try to relate this volume here to our matrix. So looking at our row 1 here, it will be represented by a vector here, that red vector here. And then row 2, in actually case here, row 2 and row 3, they're kind of overlapped each other. But for our pictorial or geometric purposes, let's look at them in these terms. So here's row 2, shown over here, and then row 3 here. So we got this 3 by 3 matrix represented by either columns or row vectors here, but they have a dimensional space, a 3-dimensional space. Okay, and then to expand on it, when you're looking at the parallelepiped here, what you do here is you just expand out your setup. It's going to have really 4 or 6 faces here and 8 vertices. So just looking at this first, this back one here, you just to understand what we're talking about, it'd be row 1 plus row 3 here, and those vectors, they'd be added together. And then over here in this far corner on top here, you'd have row 1 plus row 2 plus row 3. You just add those vectors together. And then over here, you're going to have something like row 1 plus row 2 here, and then you'd have row 2 plus row 3 here. Okay, so that's our volume that we're talking about here. And you can put that into some software package really defined by a parallelepiped here, a parallelogram. And it's going to give you those vertices, and it's going to give you the different faces and so forth here. Okay, so let's go and let's look at what I've done here. So moving down here, and all I'm showing here is those 8 different vertices or vector vertices that we have here. And those are really generated by some software, MapleSoft here, as a parallelepiped here. But what we're really looking, and the software here is going to give you the vertices for all the faces as well here. But really, we're just concerned with those 8 different faces here to understand the geometric volume here. So, okay, here's our vectors here. And we start out, make a point here when you're loading this into your software, you're going to start with 0, 0, 0 here as that first point that we're looking at. Okay, so let's move over here. So now here we're looking at it in terms of 3D here. So just say our vertical axis is our z-axis here, and then take our x and y axis here as our horizontal axis. Say x going this way, y going this way here. So when we're talking about these 8 vertices here, what we really look at is, I'm kind of showing here, color-coded here in these spheres here. So we're going to be looking at the front face, we're going to be looking at the back face, and then we got those edges or those edge faces that we're going to look at here. So looking at it in terms of looking at, say, face 1 here, we put in that first row vector shown over here, that red vector here. And then row 2, we got along our horizontal x-axis here, we got this blue row 2 vector here, and then row 3 vector. Actually, row 3 vector starts at 0 and moves over here, but if I put it in, I would be covering up the blue one here. Okay, so you can see what we're going on here. So we've got those 8 vertices here, this red one, this blue, and then we got a green here. And what we're going to note here is when we're talking about those faces here, you got to use a little bit of imagination. Say, for example, you're doing a 3D drawing here, and it's really a hidden line here that we're talking about with a face. So for that, again, that row 1 here was that red vector, and then that face here was generated because we've got these vertices here, these blue vertices, that represents, along with our red and yellow here, that represents that first face. Then again, this is in the front here, and then our second face here I've got labeled as 5 here. It's really the blue vector or vertice here, along with this blue vector or vertice, along with the green one that's shown here. The yellow is shown here. That's our vertices here, but those represent the back face here. So we got this first face here. That's really a hidden, or it'd be a dashed line here. So you got to use a little imagination. Okay, so we got the 2 faces here. Now let's move over to the back side here. Okay, same thing on the back side. I got show face 2 here and face 3 here. So again, our row 1 was this red vector here. Then row 2 would be our blue vector, and row 3 would be our green vector here. And again, we got those different vertice faces here. And in this case, you can see here our back face, I'm showing us face 2 and face 3 here. They're represented by, the first one here would be that red vector here, and then we got two yellow the red vector or this vertice here. Then we got the yellow one shown over here, yellow vertices here. Okay, so that's one of our faces, comprised of this row 1 here, and then really row 2 plus part of row 3 here. Understand that. And then our last vertice here, and then remember they match up here with this one on this other side here, so understand how they match up here. So this is the back face, so we've got that vertice shown here, so we got two faces here. We got face 2 and face 3. So we've defined 4 of our 6 faces. So the parallelogram here has 6 faces. Now the faces that we really can't show very well here are those edge faces, both the top and the bottom edge face here, those edge faces. Face 4 here would be our top face showing over here, whereas face 6 here, that 6 that is showing the bottom edge face here. And they're hard to see because this parallelogram is really squashed down, but it has some dimensions here for those 4 vertices, both on the top and the 4 vertices here in the bottom. So if we move over here, just to get an idea what we're talking about. Okay, so say for our top edge, you can see what we're talking about. You got to use a little bit of imagination here because you can see how they connect up here to top edge. You got the green one here, and then it kind of goes over to blue here, and then comes red here, and then it skips down to say yellow here because that's the bottom side here. Okay, so you can see which one. So you really got 4 vertices here, which comprise some volume we're looking at. And then, okay, so that's your top edge face. Then the bottom edge face, you can see what you're looking at here. Same thing here. You're going to have 4 vertices here. Again, you got that through that line, that face here and that face here, represented by those blue vertices here, and then the green vertices here. So you got some area to that face here, just because of the fact that you got this yellow to yellow here is on the underside of that face here. Yeah, you get the idea what's going on here. Okay, so we've got our bottom edge and our top edge shown here. Plus, we looked at those 4 other faces: face 1, 2, and then 3 and 4, or something along those lines here. Okay, and then if we move up here, and then remember, I've used MapleSoft. It's all generated, and I use the Parallelepiped here, a generation for that particular geometry here. So if we figured just the determinant on that matrix alone, we would have come up with 497,300 or 300 here, or 4.937 to raise to 10 to the 5th here. Now, that's for either the determinant or the parallelepiped. So if we would have pumped that matrix into our MapleSoft software and called out a parallelepiped, it would have given us this volume here, plus all the vector vertices and the face points, or the vertices for all the faces here. And the same thing, just by solving that matrix alone without going through all this geometry, it's going to give us the same number. So you can see our volume here that I'm showing with those 6 different faces that we have here, face, front, back, and the edges here, is equal to the determinant. So that's where we come in, and we can solve our determinant in terms of volume, so you get an understanding of the geometric equivalent here when you're talking about a determinant. So that's what we're talking about. Okay, so maybe we'll just move on and do a quick look at the other 2 points that we're looking at. Okay, now we'll just look at the 3 different points that we're looking at here for this determinant. So we'll just start with our determinant, this multivariate solution here. Now we can do a Taylor expansion against that multivariate solution, put in some points here. I'll just say x and y, which would be material and labor. Say x was 6.9 something and y was 7.8 here, and there's decimal amounts here. And we just do a second degree Taylor expansion against the determinant solution here, this algebraic solution. And it's going to give us a tangent plane here. You're going to have some z value here, and then you'd have an y coordinate here, some value for that here, and then an x-coordinate here, some value. So what you've done here is you've just taken this multivariate solution, you linearized it into a plane, and then just putting those numbers, x and y values, into your tangent plane solution here. It's really a 3D plane. You're going to get some determinant value. In this case, it's 7.528 times 10 to the 6th. And that's really this first point that we're going to be looking at. Okay, so let's just go over here and look at what we're talking about. Okay, so here's my determinant again. This is the bottom side of that determinant function that we're looking at. And we're just looking at the mid or tangent plane here, that midpoint here. And that equals 4.973 here, 10 to the 5th here, volume. That's the point that we were looking at before here. But you can see here, just following that gradient path down here, you have a change in slope, and that's where your determinant is defined at any specific point that you're looking at here. So this tangent plane is on the underside of our determinant function, because that's, if you look at it top side, you're not going to be able to see that tangent plane if you plot it out. Okay, so let's go and look at it over here. Okay, so let's just look at this midpoint here. So you can see I've put in some tangent lines here, these yellow lines. They follow that determinant value, that determinant function here that we have plotted out. So you can see it. So here's that midpoint that we're looking at. So you can see you had a change in slope here, coming down here. And where they intersect, these tangent lines here, that's the point that we're looking at. So we have a change in slope or a change in volume. And again, this is the, up here would be the beginning where we have the initial input for material and labor, and down over here on the end would be the final points that are where we'd be looking at. Okay, so going over here in terms of this parallelepiped volume that we're talking about here, remember ours was squashed down like a squashed down matchbox here. So just looking at our tangent planes here, or those volume planes that we're looking at, that first point here, then our midpoint, and then our last point that we're looking at here. So just in terms of volume, you can see here, doing that Taylor expansion against each one of these different points here. First one was 7.528 10 to the 6th here, and really that's 44 times what our last volume was here, where we had our greatest output, that last point, it was 170 units of, and 190, something like that here, versus the point here where it's 6 units or 7 units and 8 units here. And then we had the mid-range one here. So you can see we moved down from 44 times our last point here. Just to make a point here with this last point, it's 1.687 here, 168,700,000 here. Okay, so that's really our volume, and that represents the determinant here. Then that mid-range, just to go over that, it was a 497,300 here, and that's 3 times what our last value was here. And then, of course, the last one here, that 44 times here, that was 7,528,000. Okay, so that's what we're talking about when we're talking about determinants and volumes here. Okay, and in this case, we're able to look at this point here based on a tangent plane, based on a Taylor expansion. Okay, and then as finally here, just to make a point here, the determinant matrices here, you're going to have different matrices depending on your input. So that first input, remember that 7,528,000 here. We're going to have a specific determinant matrix. We're not going to go over those numbers. And then the second determinant matrix, that was at 497,300 here. So you're going to have a determinant matrix. Again, a 3x3 matrix here. And that's our matrix. And then the last one here, that was where we have a 168,700 here. So that's our determinant matrix here. So we have 3 different matrices at those 3 different points, and the matrix solution to our matrix, or the determinant matrix, equals the volume based on a parallelepiped. Okay, so that'll end our discussion.